This lesson concerns the derivative and the slope of a graph. And in particular here, I want to start off by talking about the tangent line to a graph. There's a connection here that you'll see as we go through this. Calculus includes the study of rates of change of functions, and the tangent line to a graph is connected to a rate of change, and we're going to talk about that. We know from algebra that the slope of a line indicates the rate at which the line rises or falls. In fact, some of you have probably called the slope rise over run. That's a rate of change, how much it changes horizontally versus vertically. But for a line, that slope is the same at every point on the line. It doesn't change. But for other graphs, the rate of change, or another way of saying it, the rate at which the graph rises or falls can change from point to point. So the rate of change is not the same everywhere on most graphs. For example, if we take this parabola, you can see that I've labeled 4 points on that graph, and the slope of the tangent line is going to turn out to be our measure of rate of change, and it varies from point to point, unlike on a line where it's the same all the time. It's pretty obvious from just looking at the graph that the parabola is rising more quickly at the point x sub 1, y sub 1, that lower left-hand point, than it is at x sub 2, y sub 2, the next one, or at x sub 3, y sub 3, which is at the vertex of the parabola. As we're moving from left to right, the rate of change is leveling off. It's very steep at x sub 1, y sub 1. And as you move around to the vertex, the rate of change goes to 0. And as you pass the vertex and go to the point x sub 4, y sub 4, the rate of change becomes negative and is falling off. As I said, and maybe you would have guessed on your own from this previous example, to determine the rate at which a graph rises or falls at a single point, we're going to use the slope of the tangent line at that point as the measure of rate of change. Want to be a little more formal, we could say that the slope of the tangent line to the graph of a function f at a point P, x sub 1, y sub 1, is the best approximation of the slope of the graph at that point. Because the tangent line approximates the slope of a graph at a point, the problem of finding the slope of the graph at the point becomes one of just finding the slope of the tangent line at the point. So one of our focuses here is to be able to take an equation and find the slope of the tangent line to any point on that curve. Here's an example. Suppose I wanted to find the slope of the graph f of x equal x squared at the point 1, 1. You can see a portion of the graph displayed on the right. The function itself, f of x equal x cubed, is labeled, but at the point 1, 1, the tangent line is drawn in. Now that tangent line has a slope, and the slope of that tangent line will be our measure of the rate of change in that graph at that point. And if you look at it, you can see just by looking at the graph that, and we're talking about the tangent line now, not the curve itself. The tangent line itself, if you move over 1 unit to the right from that labeled point 1, 1, and then 2 units up, you're back on the tangent line again. That should remind you of finding the slope of a line, things you've been doing in algebra for years: rise over run, change in y over change in x, delta y over delta x, however you've described it. That's nothing more than finding the slope of a line. So again, at the point 1, 1, the slope of that tangent line is 2 over 1, which is just 2. And again, we call it the slope. We describe it algebraically sometimes with the symbol dy over dx, which is read change in y over change in x. Sometimes we call it rise over run. But in any case, it's just the same old slope of a line that you've been doing for years. Now, I want to go through this briefly. We're not going to have to do this sort of thing much or maybe at all because we're going to find better ways, but I do want to at least, if nothing else, just for informational purposes and for documentary purposes, show you how this result is derived. And as it turns out, later on, we're going to find better ways to do the calculation. But I do feel the need to at least go through it once to see what would happen if you didn't have these shortcut formulas that we'll come up with later. So anyway, getting back to this problem, if you've got a graph and you're looking at a point x comma f of x, remember f of x is just another name for y, and you move a certain distance delta x to the right and delta y up, you get to another point on the curve. And that's called a secant line, the line that goes through those 2 points. Now, another way of writing delta y is just to say the change in y, f of x plus delta x minus f of x, and you can see it labeled on the graph. But the bottom line is, if you take that second point and compute the slope, what you end up with, and I don't necessarily want to follow it through step by step, but what you end up with is this equation that says the slope of the secant line is equal to f of x plus delta x minus f of x over delta x. And remember, it's really just rise over run, change in y over change in x, and we've written out what the change in y really is. So I didn't really go step by step through the derivation because it's not important to what I'm getting at for our purposes, but I do want you to see that that equation is easily derivable from the graph that we have pictured there. The beauty of this procedure is that you can get better and better or more accurate approximations of the slope of the tangent line, which is what we're really after, by moving those 2 points closer together. In other words, taking secant lines where the 2 points are closer and closer to each other. So for instance, in this original drawing I've got, you can see that you've got delta x being a certain distance to the right. But what if we decrease it? What if we let delta x get smaller? Well, what the effect of that is it pushes the points closer together. So instead of the points being this far apart, putting delta x to be a smaller value, it has the effect of drawing those 2 points closer together on the graph. If you just keep pushing that point, that second point, closer and closer to the original point, eventually you can't even distinguish the 2 points from each other, and at that point you've essentially got the slope of the tangent line. So in the limit, and that's the reason we've studied limits, in the limit as delta x goes to 0, that second point merges with the first point and the secant line turns into a tangent line. And that's the big idea. And that leads to this definition. If we take the limit of that difference quotient, or that rise over run, however you want to say it, as delta x goes to 0, we actually get the exact value of the slope of the tangent line. And this definition is just documenting what we just did in that graph. To get the slope of the tangent line, we take rise over run, and then take the limit of that as delta x goes to 0. In other words, as those 2 points come together. You might call this a derived function because we did a lot of work to get the result. And that gives this expression its name, and its name in general is a derivative. So what we're calling the slope of the tangent line has a more general name called the derivative. And you will be using the word derivative the entire semester. Notationally, if you've got a function f of x and you want to indicate its derivative, which is, by the way, the slope of the tangent line at the point x, at the point where the x-coordinate is x, you write down the name of the function, which is f. You put an accent symbol there beside the f, and you read it as f prime of x. Now there are some other notations and we'll talk about them, but that's the standard notation for a derivative. You take the name of the function and you put an accent symbol on the name of the function. So if a function is f of x, its derivative is f prime of x. I want to work an example of using this definition to find the slope of the tangent line. Keep in mind though, as I said earlier, we're going to find formulas that allow us to bypass this method. This is a very simple function, and as you'll see, the algebra is still not bad, but it's quite a lot of algebra. But luckily we have an array of formulas that will allow us to find derivatives without having to ever use this. But I want to go through at least one example just showing you what you would have to do if you didn't have the shortcut formulas that we're going to get later. So let's take this example. Find the slope of the tangent line to the graph of f of x equal 12 minus x squared. Well, the first thing you have to do is write down the formula. The slope of the tangent line is given by that limit. My suggestion, because of the ease of making careless mistakes, is to sort of take bite-sized pieces of this and do the calculation in pieces. And the first big piece is this f of x plus delta x. So I would actually go off to the side, do that calculation, and then take it and put it back into that formula. So if we go off to the side and calculate f of x plus delta x, when you're evaluating a function for some number, you plug the number in everywhere you see an x. But if you take the function and evaluate it at some expression, you just take that expression and plug it in place of x. So what we have to do is we have to take that x plus delta x and plug it in everywhere you see an x in the function. So you're going to plug it in here and here. So you find out that f of x plus delta x is equal to 12 minus, instead of being 12 minus x squared, it's going to be 12 minus x plus delta x quantity squared. And if you watch the preliminary algebra video that I've been promoting since before classes started, you'll know that you'll have to square that binomial by using the formula a plus b quantity squared is a squared plus 2ab plus b squared. So I'm going to do that where in this problem x is like a and delta x is like b. So you plug in that formula and you end up with x squared plus 2x delta x plus delta x quantity squared. Remember, the x is playing the role of a in the formula and delta x is playing the role of b. Now you have to distribute the minus sign. Be very careful about writing this out and using your parentheses and brackets so that you can do this without making careless mistakes. Now you have to distribute that minus sign. So the x squared becomes minus x squared, the 2x delta x becomes minus 2x delta x, and the delta x quantity squared becomes minus delta x quantity squared. And now you have x plus delta x, and now you can put it back into the original formula on the left column. Remember, we started off on the left column, we moved over to the side to do the piece that was the most difficult. Now we can plug it back in. So if you take that f of x plus delta x that I just wrote down and plug in the calculation that we just did, and then you take the f of x and plug in what that's equal to, which is 12 minus x squared, and very carefully do the arithmetic, you'll notice that you've got a 12 here, and you've got a minus another 12, that's going to be 0. Those will cancel out. And you'll have an x squared, a minus x squared here, and you're going to have minus a minus. Remember, those two signs are going to make a positive, and you're going to get a plus x squared and a minus x squared. So in the end, when you do that simplification, the 12s go away and the minus x squares go away, and all you're left with up top is the minus 2x delta x minus delta x quantity squared all over delta x. Now notice there's a delta x in the denominator, but there's a factor that's common to both terms in the numerator of delta x, which can also be factored out. So if you factor a delta x out of that expression, then those delta x's can cancel. And when they cancel, your whole expression just reduces down to the limit as delta x approaches 0 of the quantity minus 2x minus delta x. But remember, we're doing the limit as delta x goes to 0. So if you let delta x be 0, we end up with the final result that m, the slope of the tangent line, is minus 2x. And that's how you do it using the definition. Now it turns out, before long, we're going to see a formula that allow us to do this very quickly, almost just by looking at it without having to go through all that algebra. But right now, this is what we have. We have the definition and we used it. It requires a lot of care, a lot of consideration with being careful with your algebra, being careful about your signs, taking one step at a time, but you will get the results if you're careful. Lucky for us, later on we'll have a shortcut formula that will allow us not really to have to do that. But I did want you to see it done at least once. But before we leave this problem, let's take that result and go further with it. So what we just found out is that if you have the function f of x equals 12 minus x squared, that the slope of the tangent line is minus 2x for any x value on the curve. So I can ask some other questions. For instance, I could ask you, well, what is the slope of the tangent line to this graph at the point 3, 3? Well, once we have the slope formula, calculating the actual specific slope at that value is as easy as just plugging in. So you take the slope value that we worked so hard to get and notice that it's just -2 multiplied by the x-coordinate of whatever point we're talking about. Well, the x-coordinate of the point is 3. So you plug 3 in for x and you get -2 times 3, which is -6. So what we've done here is we've taken a fairly simple function and we've taken the definition of finding the slope of a tangent line and done all the algebra and showed how you can crank out the result. But once you get that result, it's very easy to evaluate specific slopes at specific points on the curve. The big picture here, though, is that once we move into the next discussion, we'll find that there are easier ways of calculating, and that'll make our lives easier. But in the meantime, pay close attention to everything we did. Try to understand how we related the rate of change to the slope of a tangent line. That's the most important thing, that the rate of change in a function is related to the slope of the tangent line.